So we will start from fold. So fold is a, can say, it is a structure that produced by simple compression of bed. So if you compress any bed, it will bend like this. So this is called as your fold. So in simple word, you can say fold is, you can say, bending of strata because of compression. So the generation of fold that we will discuss in genetical classification, how compressive force are able to bend any bed, or what are the required condition. Because if you compress something, the two things will happen. Either it will bend like this, it will produce a fold, or it might get shortened like this. If you compress something, it may get shortened or it may get folded. So there are different conditions where a fold will produce, that we'll discuss in genetical classification. So first we'll move to the parts of fold, different parts of fold. So first item, hinge line. So hinge line, it is the line along the fold. It is a line along the fold where the curvature is maximum. So you can say line along which fold has maximum curvature. You can see this is a fold, the curvature gradually increases and attains at some highest value, then it will decrease. So this line here, you can say it is a hinge line. It's a hinge line. So line along which you will get maximum curvature, it will be called as your hinge line. So you can take this as a fold. So fold curvature starts from here, gradually increases, will attain the highest value at this line. So this is called as your maximum curvature on a fold surface. This you can say fold surface. So this line is called as your hinge line, where the fold has maximum curvature. Or if you take a cross section, it will look like this. A cross section will look like this, and in a cross section you can call it as a hinge point. So hinge point, it is the maximum curvature at a point by taking a cross section of the fold. Cross section means if you cut the fold like this, then it will produce this type of shape, and this will be called as your hinge point. So you can say the locus of hinge point or hinge line, or the line along which will have maximum curvature. So see, the fold start to produce or start to curve from this point. It will gradually curve. At this point it will attain maximum curvature, then again that will decrease. So these points, these are called as inflection point or inflection line, you can say. And say this is an inflection line. So line along which fold has zero curvature. Line along which fold has zero curvature. Or if you take a cross section, it will be a inflection point. Like this, these are your inflection points. These are your hinge point. So these are hinge, these are, you can say, inflection point in a cross section. In a fold cross section, these are inflection point, these are hinge point, or in a 3D structure fold, you can say this is inflection line and these hinge line, this is hinge line, sorry, this is inflection line, this is your hinge line. Understood? Then the region between the two inflection, consecutive inflection point or inflection line, this is called as your fold domain. This is your one fold domain. Then another fold will start from here. This is from one inflection point to another inflection point. It is one fold. It is a single fold, you can see. And this is another fold. You can find fold in a series, you can say. So that's why this is called as your fold domain. So called as your fold domain. The point, the portion between, you can say, hinge line and inflection line. The portion between hinge line and inflection line, these are called as fold limb. Fold limb. It is the region between, you can say, inflection line and hinge line, or inflection point and hinge point. You see, the curvature of the fold will begin from here. It will attain maximum at the hinge point, then it will gradually decrease at inflection point. The sense of curvature also changes. The sense of curvature is also changes. Like this is now here, it will the sense will change like this. So at this point, the curvature sense will change at inflection point. So at inflection point, curvature is 0, and from that point, the sense of curvature will also change. And the region between these hinge point and inflection point are called as limb. So this is one limb, this is fold limb, and this is also fold limb. So these are two fold limbs of a single fold. To consider a single fold, it has two limbs. They join at hinge line, or if you take a cross section, they join at hinge point. When it comes to crest and trough of a fold, so it is, you can say, the highest and the lowest point on a fold. So highest point it will be called as your crest, lowest point it is called as your trough, or highest line along which fold has maximum height. So they may coincide with the hinge line. In some fold they will coincide with the hinge line or hinge point. In some fold they will not coincide. Here you can say this is our maximum surface, but the maximum elevation is here. Here the maximum curvature is here, but minimum elevation is here. This is crest, this is trough. If you see this fold, then crest and trough they coincide with the hinge line. So crest and trough, you can say respectively the highest and the lowest point on a fold surface. They sometimes coincide with the hinge line, they sometimes does not coincide with the hinge line. Then comes to axial plane. So axial plane, you can say it is an imaginary plane that divide the fold into two similar halves. So an imaginary plane fold into two similar halves. So mostly the hinge line and the axial plane. Mostly you can say the axial plane, it intersect the fold surface along the hinge line. The axial plane intersect the fold surface along the hinge line. See, this is a fold. So we have to insert a plane like this. So it will divide the fold into two equal half or two similar half, you can say. if you cut this along this line, or if you insert a plane along this line, it will divide into two similar half. So it will be called as your axial plane. That is called as your axial plane. It is an imaginary plane. So if this is our axial plane, so it always intersect the fold surface along this line, which is the hinge line actually. That means you have to insert any plane along the hinge line. You have to insert any plane along the hinge line, or imaginary plane along the hinge line, that will divide the fold into two similar half. It will be called as your axial plane. For the axial plane, it is not always planar. It is not always planar because the fold surface is just is not always your planar. So that's why for axial plane, it can be planar, it can be non-planar. Axial plane can be planar, can be non-planar. So non-planar axial plane, how it will be? So it we have to explain it in multi-layer fold. Suppose we have a fold like this. So if we insert an axial plane, it will be like this. Okay. This is the axial plane. So this line, it traversed along different layers. So this line is called as your axial trace. This line is called as your axial trace. So if you put any your axial plane within a fold, suppose if you are inserting anything here, so it will also intersect each page. It will also intersect each page. As these layers, they follow each other. The layers are following each other. Like I draw this layer and I'll draw the next layer exactly this shape. Exactly the layer above. So this is a condition called as your concentric fold. Called as concentric fold, where the geometry between layers are same. The geometry between layers are same. So how it will be different? So in a multi-layer fold, different layer may have different your hinge line position. Like this, I'll draw a fold like this. I'll draw a fold like this. Fold can be also like this, where here the hinge line will be here, it will be here. So if you put any axial surface, what we say, or axial plane to divide the fold into two equal half, you have to put like this. Put like this. You have to follow this. So here this will be the axial trace. Axial trace, and it is curved. It is curved. Now, if that will be that will be the axial plane, will say here, or more appropriately will say axial surface. It will be a curved one. It will be a curved one. So that's why in the axial plane can be planar, can be non-planar. Where if the axial plane is planar, the axial trace will be a straight line. The axial trace will be a straight line. And axial trace means, you can say the line, the line that joins the points where the axial plane intersect the fold surface in a multi-layer fold. So this is a multi-layer fold. So these are the points where the axial plane intersecting the different fold layers. So if it is a straight line, this will be called as axial plane. This will be called as your axial plane. And if it is curved like this, it will be called as your axial surface. So axial plane word you will only use when the axial surface is planar. If axial surface is curved, it will simple called as an axial surface, where the axial trace will also a curved line, and if axial trace is straight line, it will be axial plane. Then comes to fold axis. So fold axis, you can say it is the line along which the axial plane meets the fold surface. It is the line along which the axial plane meets the fold surface. So fold axis can only be defined along in a cylindrical fold. In a cylindrical fold, because the line along which the fold axis intersect the line along which the axial plane intersect the fold surface, that is also hinge line. That means hinge line and fold axis, they are the same line. But fold axis can be only defined in cylindrical fold. What is a cylindrical fold? So see, this type of fold are cylindrical. The fold can be like this. Okay, these are your non-cylindrical fold. This is your non-cylindrical fold. So fold can be like this also. So these are called as your non-cylindrical fold. Okay, where the hinge line is straight. Where the hinge line is straight. So hinge line can be curved. Hinge line can be curved. So if the hinge line is straight, it is called as a cylindrical fold, and in only case of cylindrical fold, we will define a fold axis. We'll define a fold axis. So that's all. That is the difference between a, can say, hinge line and fold axis, because they coincide with each other. Then another thing, suppose we have a fold here. So this we call the fold axis. You can call it as fold axis, or also this is the hinge line. So this specific line, it is called as your hinge line. This specific line, it is called as your hinge line, also fold axis. But in some concept, to differentiate between hinge line and fold axis, first you will say the fold axis is only defined in case of cylindrical fold. It cannot be defined in case of other fold, like non-cylindrical fold. And another thing, a fold axis, it can be anywhere on the fold. You can take any line parallel to the fold axis or parallel to the hinge line, that is also considered as fold axis. So these all can be fold axis. These all can be fold axis. So a fold may have infinite number of fold axis. Fold may have infinite number of fold axis, but it has only one hinge line. So that's why fold axis has specific orientation. But no fixed position. So fold axis doesn't have any specific orientation. Fold axis has a specific orientation, but doesn't have a fixed position on the fold surface. Can be anywhere on the fold surface. But in case of hinge line, it has both fixed position and specific orientation. It both have fixed position and specific orientation. So this is the difference between, you can say, hinge line and a fold axis. How we will distinguish between a hinge line and fold axis on a fold, because fold axis and hinge line, they coincide with each other. Then comes to interleave angle and fold angle. So interleave angle, it is the angle between the tangents drawn at the inflection points. It is the angle between, you can say, angle between tangents drawn at inflection points. So this is your interlimb angle. So these are, you can say, two tangents that run at the inflection points, you can say. So they make an angle this much, it will be called as your interlimb angle. Then it is your interlimb angle, today denote as I. Then fold angle, it is the angle between perpendiculars drawn at inflection point. So if you draw perpendiculars at the inflection points, they meet here, produce an angle, it is called as your fold angle. So phi. So remember, I plus phi will be 180 degree. I plus phi is equal to 180 degree. So interlimb angle, it is the angle between the tangents that drawn at the inflection point, and fold angle, this is the angle between perpendiculars drawn at the inflection points, and both add up to 180 degree. They are complementary to each other, you can say. Now comes to in a series of fold, or what we will say in a train of fold, where you will find fold like this. Alternatively, this is called as anticline, syncline. Alternatively, you will get syncline and anticline. So in a series of fold or in a train of fold, we can bound the fold by two imaginary surface or imaginary line. It is called as an enveloping surface or enveloping line. So these are two imaginary line or surface. They bound the fold. That is called as an enveloping surface. So these enveloping surface, they are imaginary line or surface that would bound the fold. Then a line that joins the inflection points. The line that join the inflection points are called median line, or in 3D you can say median surface. So it will call as your median surface or median line, you can say. And you know, this is a wavy structure. Fold is a wavy structure. So the distance between two consecutive crest or trough will be called as your wavelength. We call as your wavelength. And the distance between your enveloping surface and your median surface, it is called as your amplitude. This is called as your amplitude. Completely 2a. It's called as your amplitude. So the imaginary surface that enclose the fold, it is called enveloping surface. The line that joins the inflection points or the surface that join the inflection point is called median surface, or you can say median line. So the distance between the enveloping surface and the amplitude, the distance between enveloping surface and median surface, it is called as your amplitude. Then comes to this length or distance between two consecutive inflection point. The distance between two consecutive inflection point, it is called as your median length. So this length, you can call it median length. This is also median length, this is also median length. So the distance between two consecutive inflection point is called as your median length. So from median length and amplitude, we can define a parameter of the fold called as aspect ratio. Aspect ratio, it is amplitude divided by median length. So it will be like this. So next comes to thickness of the fold layer. So thickness, we measure in two ways. One is your true thickness, one is your apparent thickness that I have studied in case of your thickness of any layer. Here also we'll define two types of thickness. They are very much similar to your true thickness and apparent thickness. So here the layer thickness of the fold, it is measured in two ways. One is your orthogonal thickness. One is your orthogonal thickness. Another your axial plane thickness. Axial plane thickness. So orthogonal thickness, it is similar to true thickness. It is similar to true thickness, where thickness is measured by drawing perpendicular from one layer to other layer, like this. This will be your orthogonal thickness. See, this is your orthogonal thickness. You have to just draw perpendicular from one layer to other layer. You have to just draw perpendicular from one layer to other layer, that is called as your orthogonal thickness. So if this is a fold, this will be its axial plane. This will be its axial plane or axial trace, you can say. So any thickness measured parallel to the axial trace or axial plane. So we have to measure thickness that should be parallel with the axial plane or axial trace. So thickness measured parallel to the axial trace or axial plane, it is called as your axial plane thickness. So axial plane thickness, it can be a apparent thickness. So orthogonal thickness, it is measured by drawing perpendicular from one layer to other layer. It is a true thickness. It is true thickness. And axial plane thickness, thickness measured parallel to the axial plane. Thickness measured parallel to the axial plane, it is your axial plane thickness. So remember, along the hinge line or at a hinge point or hinge line, the axial plane thickness is always equal to orthogonal thickness. Here you can say here axial plane thickness is this much at this point, orthogonal thickness is different. So axial plane thickness, orthogonal thickness, they have different value at different point, but at a hinge point, both axial plane thickness and orthogonal thickness is always same. So orthogonal thickness and axial plane thickness is same at hinge point. When it comes to plunge of the fold, so the hinge line of a fold, it is not always horizontal, or the fold axis, it is not always horizontal. So here it is a fold, this is the hinge line, which is horizontal, If the hinge line, it is inclined to the horizontal, then the fold will be called as plunging fold, or you can say the fold has a plunge. So how we will consider, if the hinge line, if the hinge line of a fold is inclined, then the fold has a plunge. So if the hinge line of the fold, it is inclined from the horizontal, then the fold said to have a plunge, and then the fold is called as a plunging fold. Then you can call the fold as plunging fold. So next comes to culmination and depression. So in a fold, the hinge line can be straight, it can be curved, so it can be inclined. Okay. So when a hinge line straight, it is called as a non-plunging fold. If the hinge line is inclined or curved, in all cases it is called as your plunging fold. All cases it can be called as your plunging fold. So here you can say there is a depression along the hinge line. So any depression along the hinge line or along the, you cannot say fold axis here because it is a non-cylindrical fold. So any depression along the hinge line, it will be called as depression. Any your depression like of thing along the hinge line, it is simple called as hinge line with axial depression. Hinge line with axial depression. So it is depression. So in a depression, you can see the fold will be a doubly plunging fold. It will be a doubly plunging fold, because if you see hinge line is inclined in this part towards this direction, and in this part it is declining towards this direction. So in a depression, it is simple depression means it is a simple depression along the hinge line. It is depression along the hinge line where the fold, or you can say the hinge line, it plunges towards each other. Hinge line will plunge towards each other. Similarly, you can see here also it is a depression condition where the plunge will be towards each other. There is a condition of a depression. So a depression, or it is your elevation, in both cases those are doubly plunging. They are plunging in two directions. Here it is also plunging in two directions. If you say this is east, plunging towards east also. Along the hinge line you will get plunged towards the east. Along the hinge line you will also get plunged towards the west. So it can be a doubly plunging fold. And any elevation along the hinge line, any elevation along the hinge line will be called as your culmination. Any elevation along the hinge line will be called as your culmination. So culmination is also doubly plunging, but they plunge away from a point. Away from a point. So a fold can have only depression. It can be only have your culmination here, or it can have both. A fold can contain both culmination and depression. When it comes to deep isochords, so deep isochords is a line that joins the point of equal dips in between folded layers. So it's a line joins point of equal dip in between folded layer. In between folded layers. So this is 2 points. We can calculate the dip by drawing tangent at that point. So if you draw tangent, the angle will be, if the angle will be same, the line that joins these 2 points will be called as your deep isochords. So deep isochord, simple, it is the line that joins points of equal dip in between folded layers.